Right, so this is my demonstration video for my Sensors and Simulation module for Mechatronics and Robotics Engineering. In this coursework I'm going to be using ROS and Gazebo. Now simulation plays a huge role in robotics, and ROS and Gazebo is commonly used for that because it's a free open source operating system. It has a lot of powerful tools to help with the design and simulation of advanced robotic applications. This coursework is split into two parts, so we've got part A here, which is going to be doing some search and capture stuff in the Turtle simulator, just getting familiar with publishing and subscribing on topics and working with nodes and packages. Later we've got part B, in which we're going to design and simulate an autonomous differential drive robot to solve its way out of a maze. So you should be able to see here we've got a very basic maze which we're going to start off with. Going to get a little bit difficult, and finally we're going to add some obstacles in the way, so hopefully it'll be able to avoid these, make its way through the maze and exit the maze without crashing. Now if you look at the file structure for how I've got it all laid out, I've got a Catkin workspace in which I've created a package here for my coursework. Inside here we've got two folders for both parts. So in folder A you should see tasks 1, 2 and 3. Just an example, in folder 1 for example we've got our Python scripts in which we're going to run in the first task for the Turtle simulator. In folder B we've got our robot here, which I'll get back to, and we've also got tasks 4, 5 and 6. So just as an example, in task 5 we've got a launch file to load in the world model. We've got a script in which we're going to be running a Python script to move the robot, and we've also got our world file here. So for the challenge of task 1 we're going to spawn two turtles at random positions. One of them is going to be stationary and one of them is going to have to move and capture the other one. Now the stationary one is going to publish its own position on a topic called target, and the other one is going to subscribe to that topic and create a move to go method which is going to take in the position and calculate a move to capture it.
So this is going to be a pretty straightforward one where we only have 3 nodes, one for the target, one for the robot and one for Simscape. So the target node will publish its position on the target topic, the robot node will be subscribed to that, it'll also publish its own twist message onto the command velocity topic, and it'll also subscribe to its own pose from Simscape.
Okay, so if we explain the first task, we'll go into folder A and look at task 1. So we've got one here for my target and my robot. So this is my target. So you can see we're writing this in the Python language. What we want to do is create a class for the turtle bot, and we're going to run this init method in which it creates its own node, wipes the monitor, and this is where we're going to generate a random integer between 1 and 10 and spawn it on the x and y axis. We're going to create a pose type message, and we're going to assign the x and y value to the random integers which we've already generated, and we create a publisher topic here in which we create a publisher of the name target. It sends across a message of a pose, and whilst the node is continuously running we're going to publish the pose onto that topic. Okay, so this is the robot script, so it's a little bit more complex because this is one that actually has to capture the target. Again, we create an init method in which it defines a couple of things such as its publishers and its subscribers. So you can see we've created a pose subscriber in which every time the Simscape publishes the robot's pose, it's going to pick it up and call this callback method here called update pose. This update pose here is basically just going to update the robot's position in the script. We've also got another subscriber which subscribes to the target topic. Again, this is with a pose, and it calls another method for coordinates, which is basically just going to update us on where the target turtle is. Also, we want to set up a subscriber for the velocity. This is called the command velocity, in which we send a twist. So we send a linear velocity, and we also send an angular velocity in which we're going to move this turtle. We've got a method here for spawning the robot. Similar to the target file, we're going to generate a random number between 1 and 10 and spawn that on the screen. And we've basically got some math functions here which is going to take in the robot's position and the target's position, calculate the Euclidean distance, what the velocity should be for its linear, the steering angle and the angular velocity. This is our main method in which we're actually going to move the turtle towards its goal. So we run a while loop here, so whilst the turtle has not captured its target, we're going to set some values for the linear velocity, the angular velocity, and at the end of it we're going to publish the twist type message to Simscape. Here in the main method we've got a try catch here, which is basically we're just going to create an instance of the turtlebot class, spawn it at a random position and move it to goal.
So if we run our first task, we first need to run ROScore and then run the turtle simulator. And if we open up a new terminal and go into our task 1 package and run the MyTarget Python script, you'll be able to see that the monitor will be wiped clean and it'll spawn a target at a random position, which in this situation is 8.2. Now if you use the ROS topic list command, you should be able to see that we've created our own target topic here. It's automatically created a MyTarget command velocity, but we're not going to be using that this task as we're not making it move. If we look at the ROS topic info for the target topic, We should be able to see that it's sending a message across of type pers, but there's only one publisher for the MyTarget node. We've currently not got a subscriber because we haven't run the robot script. If we run the robot scripts now, you should be able to see that it'll spawn another random turtle at this position and move towards the target. Once the robot gets within a 0.01 tolerance of the target, it'll cancel out the linear velocity. Now if we look up on the ROS topic info for the target again, you should be able to see that we've now got a subscriber, which is the robot node. Now one way that we can visualize the nodes and the topics is by running an RQT graph. If we run this, it'll show us that we've got 3 nodes for the target, the robot and the simscape. So the target is publishing on the target topic, and that's being subscribed to by the robot. The robot then sends over its command velocity to the simscape, and it subscribes to the pers.
Okay, so moving on to the next task. It's very similar to the first one, however this time we're going to add some movement to the MyTarget turtle. Therefore the aim of this one is that the robot's still going to chase the target, however the target is going to pick somewhere on the turtle sim window that's going to take it away from the robot. Therefore we need to create a subscriber for the target that's going to take the position of the robot. The way that I'm planning on doing this is basically splitting the turtle sim window into 4 quadrants, so half vertically and half horizontally. Depending on which corner of the turtle sim window the robot is, the target is going to calculate a position to either one of the 4 corners. From here we'll use the move to goal method again to take it away from the robot.
Okay, so this one's going to be slightly more complex. We're still going to have 3 nodes, one for the target, one for the robot and one for simscape. So simscape is going to automatically publish the robot pers, to which the target node is going to subscribe to that topic. The target node is going to publish the command velocity to the simscape to actually make it move in the turtle sim window. The robot also needs its own pers, so it subscribes to the robot pers topic, and it's also going to publish on its command velocity topic to make it move in the simscape window. And finally, because the robot's chasing the target, it needs its position, therefore it's going to subscribe to the target pers topic to get that.
Okay, so if we look over the code for the second task, the robot turtle is going to virtually stay the same because it's still going to be chasing the target. However, on the target, what we need to do is add a subscriber to the robot's pers, so here you can see that I've subscribed to the robot to pers topic. It's a type pers, but it does use this callback for the update in the robot's pers. Inside here, I basically update the robot's pers, but this is where I calculate which corner of the turtle sim window to move towards. So just an example, if the robot's X position is less than 5 and its Y position is greater than 5, then it's going to be in the top left corner. Therefore the goal pers is going to be in the bottom right corner, which has the coordinates 10, 1. And from here I'm going to put the goal pers parameters into the move to goal function, and this should be moving the turtle on the simscape window.
Okay, so to run this task we need to open the terminal, run roscore and run the turtle sim. We also need to go into the task2 package and run the mytarget2.python script. So it's going to spawn a turtle in a random position and it's going to move to the center of the screen. From here we can open up a new terminal and launch the other Python script for the other turtle. You should see that again it will spawn at a random position and the target turtle will move away from the robot into the opposite corner. Again, to get a visual of the nodes and the topics, we can launch RQT graph to get a visual of which nodes are publishing or subscribing on each topic. So we've got 3 nodes for the target, robot and the turtle sim. The target is publishing on the command velocity and it's also subscribing to its own pers. The robot is subscribing to the target pers, but it's also publishing on its own velocity.
Okay, so moving on to the raw stuff with task 4. We're going to start off with this very basic maze where we're going to build it in the model editor. I'm going to create a robot with an onboard laser scanner, integrate it with the ROS gazebo with a launch file, and do the robot navigation from point A to B, which is basically just one side to the other side of the maze.
My differential drive robot had 2 wheels and a caster wheel, so I put a quick sketch together to come up with the dimensions for the robot. Okay, so when working with a laser scanner, the 2 things that need to take into account is the angle of detection. So on this one here, we're going to be working with 180 degrees, and also the sample size. So on this drawing here, we've got a sample size of 13. Whereas for my coursework, I'm going to be using a sample size of 180. I'm also going to split it into 5 different regions. So we're going to end up with left, centre, centre right and right. Now what the laser scanner is going to do, it's going to run through every sample in each region and return the shortest distance so it knows when something's in front. I'm going to create 2 variables, one for an inner radius and one for an outer radius.
So I've built my robot here in this SDF file. Now each individual part of the robot has its own visual tag and its collision tag. So just as an example, you've got the right wheel here, which has got a visual and its collision. Now as the right wheel's a cylindrical shape, we've got a radius and a length that we've got to define. A bit further down, I've attached the Hakuyo sensor, which is going to help us to detect the proximity. Now if we launch Gazebo, now that we're in Gazebo, I'll input this robot and put it in the middle. Now everything within this blue range is everything that the robot can see, so you should be able to see it's got a detection range of about 180 degrees. If we zoom in on the robot, you should be able to see that we've got 2 wheels at the front, you've got a caster wheel at the back, and we've got the Hakuyo sensor on the top. If, for example, we take a cube and put it in front of the robot, it should be able to detect it. So the cube's sending out a total of 180 samples. If we go into the topic visualization, we should be able to see how far away the cube is. If we look on the scan topic, so this is the scan topic. You can see that it's got a detection range of 180 degrees. If we zoom in to where it's detecting the cube, you'll see that the closest point on the cube is about 2.3 meters away.
So getting started with the most basic maze, we're going to run a launch file inside the task 4 package. It's going to open Gazebo with the basic maze in and the robot in the starting position. So again, everything within this blue range is what the robot can see. Now I'm going to run a Python script inside this task 4 package. Now this real simulation would take a couple of minutes, so I'm going to speed it up. But the easiest way to solve its way out of a maze is basically to hug one of the walls. So in this situation, I've programmed the robot to slightly bounce off the left hand side. Task 5 and 6 includes a slightly more complex maze in which the robot has to turn itself right and left. Here you can see I'm assigning a floating point number to the inner radius and the outer radius, and in this flowchart it demonstrates the logic in which the laser scanner takes in the input and calculates which manoeuvre the robot's going to take. Inside the Python script for moving the robot, it's going to consist of 7 manoeuvres, so we've got 1 manoeuvre for moving it straight, 3 manoeuvres for moving the robot right, and 3 manoeuvres for moving the robot left. On the right here we've got the 3 right turns, and I'm just going to demonstrate in the logic where these would be used. So first off, if the minimum distance in the left range is greater than the radius, so there's nothing in that area, the centre left is less than the outer radius, so there's something blocking this area, and in the centre range there's nothing there, the robot's going to take a medium right manoeuvre. Secondly, if the minimum distance in the left range is less than the radius, so there's something in this area, the centre left range is less than the outer radius, so there's something within this range here, and the centre range is also less than the outer radius, so there's something in the centre range. The robot's going to execute a sharp right manoeuvre. Finally, if the minimum distance in the left range is less than the radius, so there's something within this area, however there's not something detected in the centre left or the centre range, we're going to take a slow right turn. So to run task 5, we need to run this launch file within the task 5 package. It's going to load up Gazebo with the maze and the robot in the starting position. Then we launch the Python script, which is going to move the robot. This simulation will take roughly 9 minutes, so I'm just going to speed it up to show the robot turning right and left to solve its way out of the maze. Now task 6 is the maze with obstacles, but by running the same algorithm we should be able to avoid these collisions. By looking at it from a top view, you should be able to see that we've got 4 extra obstacles that we've got to avoid. Finally, we run the last Python script, which is going to move the robot, and you'll see on the first obstacle it's going to detect it and slow down a little bit. After this, it's going to reach the second obstacle, see that it's in the way and turn right. Now it can't go through this gap on the left because the third obstacle is there. So what it's going to do is it's going to solve its way around the top right hand corner of the maze, detect the fourth obstacle and exit the maze.